Compact conductors differ from conductors in several ways. Firstly, consider the construction. Conductors are made of individual round or shaped strands twisted together to form a conductor. Compact conductors, on the other hand, have strands that are shaped and compacted to reduce air spaces between them, resulting in a more compact and dense conductor. Secondly, the current carrying capacity. Compact conductors have a higher current carrying capacity for the same conductor size due to their reduced resistance and increased surface area. Thirdly, the inductance. Compact conductors have lower inductance than conductors because of the reduced air space between strands. This results in less voltage drop along the conductor and improved circuit performance. Fourthly, flexibility. Compact conductors are less flexible than conductors due to the compaction of strands, and this can make them more challenging to bend or handle during installation. Fifthly, physical dimensions. Compact conductors typically have a smaller diameter and cross-sectional area than conductors for the same current carrying capacity. This can save space in cable trays and conduit systems. Sixthly, the cost. Compact conductors are generally more expensive than conductors due to the additional manufacturing process required to compact the strands. Compact conductors are commonly used in applications where high current carrying capacity, low inductance, and reduced size are important. Some specific applications include high power transformers, generators, power distribution systems, and industrial motors and drives. The reduction of airspace within the conductor construction is a key factor contributing to the enhanced performance of compact conductors. This reduction in airspace directly influences several electrical characteristics. The higher current carrying capacity arises from the increased density of the conductor, which provides a greater cross-sectional area for electron flow within the same overall conductor size. The reduced resistance, also resulting from this increased density, minimizes energy loss in the form of heat, allowing for more efficient power transmission. The lower inductance is a consequence of the closer proximity of the strands, which reduces the magnetic field generated around the conductor. This lower inductance is particularly beneficial in applications where minimizing voltage drop and improving circuit response times are critical. While compact conductors offer numerous advantages, their reduced flexibility can pose challenges during installation, particularly in tight spaces or complex wiring configurations. Therefore, careful planning and consideration of the installation environment are essential when selecting compact conductors. The smaller physical dimensions of compact conductors can be a significant advantage in applications where space is limited. This is especially true in cable trays and conduit systems, where minimizing the overall size of the wiring can reduce installation costs and improve space utilization. The higher cost of compact conductors is a trade-off that must be weighed against their performance benefits. In applications where high current carrying capacity, low inductance, and reduced size are paramount, the increased cost may be justified. However, in applications where these factors are less critical, conductors may be a more cost-effective option. The National Electrical Code, or NEC, provides guidelines for the safe and effective use of both conductors and compact conductors. It is important to consult the NEC and other relevant standards to ensure that the selected conductor type is appropriate for the specific application and that all installation practices comply with applicable regulations. When comparing conductors and compact conductors, it is crucial to consider the specific requirements of the application, including the current carrying capacity, voltage drop, inductance, flexibility, and space constraints. By carefully evaluating these factors, engineers and electricians can select the most appropriate conductor type to ensure optimal performance and safety. In power distribution systems, for example, compact conductors may be preferred due to their high current carrying capacity and low inductance, which can minimize voltage drop and improve system stability. In industrial motor applications, compact conductors may be used to reduce the size and weight of the motor windings, which can improve motor efficiency and performance. In high power transformer applications, compact conductors may be used to minimize the size and cost of the transformer. When working with conductors and compact conductors, it is essential to use appropriate tools and techniques to ensure proper installation and termination. This includes using the correct stripping tools, crimping tools, and connectors. Proper installation and termination are critical to ensure the safety and reliability of the electrical system. Regular inspection and maintenance of conductors and compact conductors are also important to ensure that they are in good condition and operating properly. This includes checking for signs of damage, such as cracks, corrosion, or overheating. Damaged conductors should be replaced immediately to prevent electrical hazards. Choice between conductors and compact conductors depends on a variety of factors, including the application requirements, cost considerations, and installation constraints. By carefully evaluating these factors, engineers and electricians can select the most appropriate conductor type to ensure optimal performance, safety, and cost-effectiveness. The difference in flexibility is also a consideration for maintenance. Over time, conductors may need to be rerouted or replaced, and the comparative ease of handling conductors during these procedures should be considered in the initial selection process. Conductors can be easier to work with in tight spaces or when making connections in existing equipment. When considering cost, remember to factor in not just the initial purchase price but also the long-term operational costs. Compact conductors' higher current carrying capacity and lower inductance can lead to reduced energy losses and improved efficiency, potentially offsetting the higher upfront cost over the lifespan of the installation. It's also important to consider the environmental conditions in which the conductors will be used. Factors such as temperature, humidity, and exposure to chemicals can affect the performance and lifespan of both conductors and compact conductors. Choose a conductor type that is suitable for the specific environmental conditions to ensure long-term reliability. In summary, the key differences between conductors and compact conductors lie in their construction, current carrying capacity, inductance, flexibility, physical dimensions, and cost. Compact conductors offer advantages in terms of current capacity, inductance, and size, while conductors are generally more flexible and cost-effective. The selection of the appropriate conductor type depends on the specific requirements of the application and a careful consideration of the trade-offs between performance, cost, and installation constraints. Always consult the NEC and other relevant standards to ensure that the selected conductor type is appropriate for the specific application and that all installation practices comply with applicable regulations. Understanding these differences is crucial for electrical engineers and electricians to make informed decisions and ensure the safe and efficient operation of electrical systems.